Alright, partial fractions, so let's look at some. There's a few different versions of the partial fractions depending on what we look at, starting with looks like. So this first one is what I'm going to call distinct. Oops, not distinct. Linear factors. Yeah. Alright, so an example might be we want to find the antiderivative of, say, 3x plus 5 over x plus 1 times x plus 3 dx. Now this one's already factorised, they might not always already be factorised. So essentially what we want to do is we want to split this up into two fractions. One of them which has a denominator x plus 1 and the other one which has a denominator of x plus 3, because what we're going to use is we're going to use the 1 over x when we're to log e, we're using that in the end for these things. So first thing we've got to do is resolve into partial fractions. To spell it properly, resolve into partial fractions. All right. Spelling's terrible too. All right, so what that means is that we want to split up this into two fractions. So make it equivalent to, that's why I've used the 3, to some fractions where one of them has a denominator of x plus 1 and the other of x plus 3. And there will be some numbers on the top. All right. So I'm going to. Well, I'll go through this first one, and then others I'll use the calculator for. All right. So what we then now need to do is we need to say, okay, if this one here, if they're equivalent, then the denominators, let's make the denominators the same. Then the one on the left here, I need to multiply that a by x plus 3, and I need to multiply that b by x plus 1. And so then if these things are equivalent, the denominators are the same, then our numerators have got to be the same. Alright, so this is turning into partial fractions. Remember this from last year? Yes? No? Maybe? Don't remember it at all. Alright, okay. Didn't do it?
Not that I remember.
Alright, so yeah, so as I said, basically we're splitting it up so that we've got two easy things to work with, same kind of idea. And so this is called partial fractions. So we're turning into, and these are the other fractions, the partial fractions. But they're the same thing. So if they're the same thing, our numerators we've already got the same thing, then our denominators we've already got to be the same, and our numerators have got to be the same. So that means that 3x plus 5 is got to equal a x plus 3 plus b x plus 1. Now there's a couple of different ways that you can proceed from here to find out what numbers this a and b are. One of them is to expand, collect your like terms and then create some equations and solve simultaneously. That's what I'm getting at. The other way is to do a bit of a tricky thing, because this is plus 3 here, if I put minus 3 in for x, what's going to happen to this term there? Yeah, we'll go. So rather than expanding collecting like terms, I can say, okay, so let's let x equal minus 3. And if I put that in, I'll get 3 times minus 3 plus 5 equals a. And yeah, minus 3 plus 3 is 0. Oops, plus b minus 3 plus 1. Negative 9 plus 5 is negative 4. That's 0, of course, so that's gone. Equals negative 3 plus 1 is negative 2. So from that we can get that b's got to be 2. And then if we have a look at this other one over here, and we say, okay, because that's plus 1, if I put negative 1 into there, this term's going to go. Alright, so I substitute. So we're not substituting random numbers here, we're having a look at what our brackets here, our factors are, and we're choosing numbers that make one of those equal to 0. So we've got 3 times negative 1 plus 5 equals a times negative 1 plus 3 plus b times negative 1 plus 1. That's the bit that goes. So we've got negative 3 plus 5 is 2. Minus 1 plus is 2a, so a is 1. So, from that, we've got then that 3x plus 5 over those two brackets, x plus 1 and x plus 3, will be equivalent to a, which is 1, over x plus 1, plus b, which is 2, over x plus 3. And so now, when we go to our integration here, we can say, all right, if these two things are equivalent to each other, then we can say that this integration, replace that by what? The 1 plus over x plus 1, I should say, plus 2 over x plus 3 dx. And so now we've got two things that are more easy for us to anti-differentiate. And so, as I said before, an antiderivative of 1 on x is log to the base e. So we've got two separate bits. So when I anti-differentiate 1 on x plus 1, it will be log to the base e of x plus 1. And when I anti-differentiate 2 over x plus 3, it would be, the 2 would be there. And then log to the base e, x plus 3 plus some constant. Alright, and then we can fiddle around with some log laws here.
So when you find the, when you're finding the antiderivative of log, you always put the modulus on?
Yeah, I always put the modulus on, because you can't take the log of a negative.
Yeah. Okay, that makes sense, yeah.
Alright, now sometimes what's in here
Will be negative.
will always be positive anyway.
Yeah.
So like, for example, if it was, well, which is going to happen in this next step. So when I put that 2 up here, log to the base e, magnitude of x plus 1, this log to the base e of x plus 3, well, when we square it, that's always going to be positive. So for that, it's not necessary to have our modulus, because it's always going to be positive anyway.
Yep.
All But I still need it here with the x plus 1, because
Yeah.
that could be negative. Plus some constant, and then you can whack them together with another log law. So that's the magnitude of x plus 1 times x plus 3 squared plus some constant. Alright, so again, the same thing as we've been doing last week when we were doing the substitutions to make something simpler. So now we're using these, what's called partial fractions, to make it simpler. Alright, so you've got the calculator thing. Alright, so with this next example, here's another calculator sheet that we're going to use to help us. So again, question in exam 1 is partial fractions. Whether they'd actually ask you a question where you're going to have to do all of that stuff, or whether they would word it in some way to lead you into, like they might, exam 1, they might give you this and tell you to show that this is this, and then go hence or otherwise find the integral of. So yeah, whether they'd actually get you to do all of that in exam 1, I'm not sure that they would, but they could ask you a question along those kind of lines by phrasing it in a particular way. All right. Exam 2, of course, you've got your calculator, so you use your calculator to do it, and I'll show you a couple of things with the calculator now. Alright, so if you have, so the next one we're looking at is if something's an improper fraction. So, and if something's an improper fraction, so for example this one here, x to the 5 plus 2, whoops, over x squared minus 1, yep, x squared minus 1 dx. Now you notice here that on the top here, the power of x, power of 5, and here it's x squared on the bottom. So because the power up here is greater than here, it's considered to be an improper fraction. And so before we start, we need to divide first. Alright, so when we do that, there's a couple of things that we can do. So we can either do our long division, or we can use our CAS, which is what I'm going to do now, to do that. So, that sheet I've just given you, the polynomial division. So if you go to action, advanced, no, not advanced, transformation, I'm transforming. I'm transforming a fraction into what we call a prop frac, or a proper fraction. And so then it comes up with the prop frac, and then you can enter the stuff. So if you go to the keyboard, fraction template, where we got x to the 5 plus 2 is our numerator, our denominator is x squared minus 1, and we're going to prop frac that. I don't think I need to put x or anything, no I don't. And then there it is. Alright, so in our calculator gives it to us in a slightly different form than what we really are looking at. So x to the 5 plus 2 over x squared minus 1, according to the calculator, is the same as x cubed plus x. And then our calculator separates the next two terms that I'm going to put together, separates them. But I'm going to put it together because the denominator is still the same, and that's x plus 2. Alright, so by dividing it out, we've now got these things. So these first two bits, we can anti-differentiate them easily enough. It's this one on the end. So this one on the end here, we need to do partial fractions. Right, on that bit. So I'm going to use the calculator again to find out what this bit here is in partial fractions. Alright, now just before I do that, when you have a look at this, the denominator is x squared minus 1. So if you do a dots on that, you'd get x plus 1, x minus 1, wouldn't you? So when we do our partial fractions, it's going to be 2. And each one will have, one of them will have x plus 1 as the denominator. The other one will have x minus 1 as the denominator. Alright. So rather than going through that process I did in that first example, let's do our partial fractions. Alright, so to do that, and there may be other ways of doing it, but this is the way that I do it, is that you put in the thing you want to do as well. So I'm using the fraction template, and then that's x plus 1, 2 I should say, over x squared minus 1. Alright, then go here and I highlight that. So, and I'll tell you why in a minute. I'll highlight it and why I've put it in there. You don't have to, but I'll tell you why I've done. So this time we use the interactive, and we are transforming again. So we're changing it into partial fractions. Now this is expand. We're going here, expand. And now, see here, we've now got two options. We expand the expression or partial fraction. Now we want partial fraction. You'll notice the expression, you'll notice the one that I put in and highlighted is now already there. So I find that it's easier to type the thing in the main screen than it is into this little box. Then what's our variable? Our variable's x. And then we go OK, and there it is. Alright, so negative a half, x plus 1, plus 3 over 2, x minus 1. So our a and our b, negative a half, 3 over 2. Alright. So when we come back over here then, coming back over here, we can say that x to the 5 plus 2 over x squared minus 1 is the same as x cubed plus x plus that's this stuff on the end that we found out to be, well, plus, I probably should put minus there, 1 over 2 x plus 1 plus 3 over 2x minus 1. Alright, so now let's do our antiderivative then. So the antiderivative of that, because these are equivalent, the antiderivative of this on the left would be the same as the antiderivative of what we've got on the right there. So the antiderivative of x to the 5 plus 2 x squared minus 1 dx will be the same as the antiderivative of all this stuff. Alright, now because we've got 4 terms, we can split it up into 4 parts if we want to. But I'm not going to write that line, I'm just going to anti-differentiate each of these. So x cubed would become x to the 4 on 4, yep. X would become x squared on 2. Alright. This here, 1/2, so 1/2 is just a factor. And the 1 over x plus 1 bit becomes log to the base e. Oops, so x plus 1. With me on that one?
Yep.
Yep. And the other one, 3 over 2, treat that again as just a factor, 3 over 2. What is it? It's 3 over 2 times 1 on x minus 1, so log to the base e, x minus 1, plus some constant. Alright, then we can muck around with a few things. So x to the 4 on 4, plus x squared on 2. Minus 1/2, log to the base e, x plus 1. Going to bring the cubed up here, leave the half out the front. Alright, I'll leave the modulus in there because if you cube a negative number you get a negative. And I'm going to take the minus out here as a common factor, not the minus, the half. Plus the half. So then I've got log to the base e, x minus 1 cubed, minus log to the base e, x plus 1. And if I've got a minus, I can put them underneath each other, so final neatening up. Well, whether it's neater or not sure. But anyway, log to the base e of magnitude of x minus 1 cubed over the magnitude of x plus 1 plus some constant. Right, anything about that? I went through too quick. No? All right. Right, the next one involves if what we say has repeated linear factors. And so something which has repeated linear factors, here's an example. And when I'm talking about these repeated linear factors and things, for all of these I'm talking about the denominator. So here it's x plus 2 squared. Well, we know that x plus 2 squared is x plus 2 times x plus 2. So there's a linear factor and it's repeated, it's there twice. All right, so when we express these as partial fractions, I'm going to do most of it. To express as partial fraction, what we need to do is we need to have all of the possible factors represented. So in this case, when we have 3x plus 1 over x plus 2 squared, so we have to have all of the factors represented. Well, one of the factors is clearly x plus 2, but the other factor, so the other thing that divides evenly into x plus 1 squared is in fact not x plus 2 squared I should say, is in fact x plus 2 squared. So when you have repeated linear factors, you can have the linear factor, but then you've got to have the product of those linear factors as well. Alright, and so then we do partial fractions. Want me to do that one by hand, or are you happy with the calculator?
Use the calculator.
Happy with the calculator? Alright, so if we use the calculator...
Sorry? Is that
it's meant to be B, yep, sorry. My bad, B. Alright, so if you do this by hand, you do that first example I did, you'd follow that process. But if you use your calculator, then say there's some stuff down in there, what you find is that A is 3 and B is -5. Alright, so if that's the case, then the antiderivative of 3x plus 1 over x plus 2 squared is the same as antiderivative of this one here, and A is 3. So 3 over x plus 2 plus, well, it's -5, so minus 5 over x plus 2 squared dx. Now, while that doesn't seem to be simpler, it is in fact simpler because up here, over here, we had an x up there on our numerator, and both of these no x in the numerator, so that simplifies things. This bit here is what it is. 3 times 1 on x plus 2. This is -5 times x plus 2 to the -2. Yes? So this one here, we use our polynomial, and because using the chain rule in reverse, derivative of what's inside here is 1, yep. So this is 3 log to the base e of x plus 2 minus 5. It increased the power divide by the new power. Yes?
Why wouldn't you? Oh, is it because it's squared you wouldn't do logs?
Yeah, because it's squared.
Yeah.
Because the problem it's to the -1 that we have. Right, so the power of -1, that's where it goes to the log. All other powers are just polynomials. The polynomial pattern.
Okay.
All right, so I can put the, well, let's just leave the 3 there. Because we've got no other log bit. This minus and this minus give me a plus, and 5 over x plus 2 plus some constant. All right, there's one more example. And the one more example is to do it as partial fractions. To do it by hand is quite complicated. I've done it by hand here. It goes for a page and a half. So I'd be guessing that probably not going to be an exam 1 type question. So it's something if we, what we call an irreducible quadratic factor. So what we mean by that is that we can't factorise it. So irreducible means we can't factorise. So, here's an example. All right. If we were, and I'm going to use the calculator to do it for us, but if we were to do it by hand, and as I said, it's quite long here on my word solutions, to turn that into a partial fraction, again, we're going to end up with 2 fractions with these 2 factors. This first one's easy enough, that's A. But in this second one here, because there's a x squared power there, the top here becomes a little bit more complicated. It actually needs an x 1 power less. So it needs bx plus c on the top. Because we've got a squared here, whenever we're looking at what is on our numerator, it's going to be 1 power of x less than what we've got in our denominator. Alright, so that makes the calculation a bit more complicated. So I'm going to use the calculator to do it. So we go there and we, excuse me, 4 over bracket x plus 1, close the brackets, x squared plus 1, highlight it, interactive, transformation, expand, partial fraction, x. And there it is here. So, according to our calculator, that is 2 over x plus 1. And what have we got? Minus that there. 2x minus 2 over x squared plus 1. So onward work solutions. Going from here to here is 3/4 of the page. So it's just a lot of, you can have a look at them later if you want to have a look. So it's just a lot of algebraic manipulation. Alright, so now we're going to anti-differentiate this one here. Alright, so an antiderivative of, or an antiderivative of is the same as 2 over x plus 1 minus 2x minus 2 over x squared minus 1. Now, what else I also need to do is I need to split this here up into 2 bits. Alright, so I need to split this into its 2 parts. So, minus 2x on x squared take 1. Minus 2, minus and a minus is a plus.
Is it plus 1?
Plus 1.
X squared plus 1.
It is 2, I've forgotten that. Thank you. Alright, with me so far?
Yep.
Yep. Alright, first bit's easy enough to do, isn't it? Yeah. This one's easy enough. This one here.
Making polynomial.
Well, what do you notice about what's on top?
No, 2x.
The derivative of is 2x,
Oh.
isn't it? So that's where we would use what we did last week. Let u equal x squared plus 1. Yes? No? Maybe?
Yes.
Yes? Alright, so that's, so for shortcut there, this first one here, the 2's there, log to the base e, x plus 1. And yeah, because that's the derivative of this. So when we anti-differentiate, will be, now, x squared plus 1. Something squared plus something squared.
Difference of x squared.
No, plus, not
Oh,
different.
sorry.
Something squared plus something squared. Ring any bells?
Sorry.
Inverse circular?
Oh,
Tan, yeah. Yep, something squared plus something squared. Tan, inverse tan, inverse tan. Inverse tan of what? Inverse tan of
1 over
x.
how's it 2x on the top though?
Well, that's where we go. Do that over here. Right, yep, I'll work through that. So that's where we go, okay, so now we've got minus 2x over x squared plus 1 where we let u equal x squared plus 1. Sorry, that's not what we let u equal. We let u equal x squared. And then we've got du dx equals.
Would it matter if you let u equal x squared plus 1?
Yeah, it does, because you don't get the tan minus 1 bit.
Oh, yeah.
So du dx is, so that means that dx is du on 2x. And so the integral with the negative out the front, u squared plus 1, and dx is du on 2x. 2x is cancel. And so you got the negative 1 over u squared plus 1. And the tan, inverse tan one, is a over a squared plus, in this case, u squared. Du,
Yeah. So it's tan.
negative tan minus 1 of u squared there, so tan x. Alright, so that's where we get that one from, minus tan x. And then this one over here, because it's irreducible, it's treated as 1 over x squared plus 1, which is 1 over something. 1 over something goes to log.
For 6E, the work solutions would be this stuff, but
And then over,
But why didn't you do that for the other,
I think
for the previous example?
That's fine.
why didn't I do that for the previous example? The previous example,
Oh, no.
because it was a difference of perfect squares.
Do you need the model?
Actually, don't need it, do you?
What do you mean it was?
Previous example was x squared minus 1.
No, it was x plus 2 squared, all squared.
Yeah, because it was all squared, and this one's just the x
One
is squared
squared.
plus 1. All right, now I've lost a minus somewhere. I've lost a minus. Oh, here. That minus should be there. Silly of me. And I've... Yeah. All right, so what do we got? I've put these two things together. And I'll do that. I've got this. I've got that. All right, so yeah, there's a fair bit of stuff in
Does it
all of
matter
those.
which
That
one?
one's pretty complicated.
Does it
Sorry?
matter if x squared plus 1 or x, or the modulus of x
Oh,
plus 1?
actually, I've got them the wrong way around, haven't I? Sorry. Yes, you're right. The other way around. Yeah, because that's the minus. That should be underneath, shouldn't it?
And does the 2 cancel out or not?
The 2's the common factor, so I'll put it at the front.
So if they weren't a common factor, you wouldn't be able
You
to...
wouldn't be able to combine it, yeah. So I've moved those two things next to each other. I've taken the 2 out as a common factor, and then that over that. It's better.
Why did you change it from minus to? Oh, plus 2 minus. Okay.
No, because it's minus 2 here.
But isn't, what about the minus in front?
That was already there.
Yeah, good point. Good point. Yeah, it is plus there. Yeah, it is plus. I don't know what I was looking at. I was looking at the wrong thing. Yes, it is plus. So that's plus. So if they're plus, they get multiplied together. Don't they? And you don't need the modulus around there because that's always going to be. Yeah, because sorry, this minus out the front here is you're taking away all of that. So you're taking away 2x and you're taking away negative 2's. Yeah, I've written things in different orders here, that's why I've confused myself. Yep. All right, and there's our final answer on that one. All right. So yeah, something that's really quite complicated. So I'll be thinking that exam 1 is not going to be very time consuming. I would doubt that we would get something as involved in that. However, they could pull bits and pieces out of it. All right. 7G.
These guys can swap.
Yeah,
They can be arranged to do that.
Two plus 1.